Right now, as you're listening to these words, you're traveling through space at over 1.3 million miles per hour. You're spinning with Earth's rotation, orbiting the Sun, racing through the Milky Way galaxy, and hurtling through an expanding universe toward destinations you'll never reach in countless lifetimes. And here's what should make your mind reel with wonder. Despite this incredible cosmic journey, you occupy a position so infinitesimally small in the grand scheme of existence that if the universe were the size of Earth, you wouldn't even register as a single atom. Before we dive into the mind-bending scales that await us, I'd love to know where you're tuning in from tonight and what draws you to contemplate the vastness of existence. And if you find yourself captivated by these cosmic mysteries, I'd be grateful if you gave this video a like and subscribe to join our community of fellow space explorers. Get ready. The journey begins now. Tonight we're embarking on the most humbling journey human consciousness can take. We're going to explore a question that has haunted our species since we first looked up at the night sky and wondered what lay beyond those distant points of light. How big is the universe? And by the time we're finished, you'll understand why this isn't just a question about measurement, but about the very nature of reality itself. The story of humanity's understanding of cosmic scale reads like the greatest detective novel ever written, where each clue leads not to answers, but to even more profound mysteries. Picture our ancestors 5,000 years ago, standing beneath star-filled skies that seemed close enough to touch. To them, the heavens were a dome, perhaps just beyond the highest mountains, decorated with lights that served as guides and gods. The entire universe, in their understanding, could be crossed by a determined traveller in a matter of weeks. This wasn't ignorance. This was the logical conclusion of careful observation with the tools available to them. The moon appeared roughly the same size as the sun, suggesting they occupied similar cosmic real estate. Stars seemed to move as a single, unified canopy, implying they were all equidistant from Earth. The entire celestial sphere could be encompassed by human vision, making it reasonable to assume the universe itself was similarly comprehensible in scale. But then came the ancient Greeks, and with them, the first hints that reality might be far stranger than appearances suggested. Around 270 BC, a brilliant mathematician named Aristarchus performed an elegant geometric calculation using shadows and angles during lunar eclipses. His conclusion was startling. The sun was not only much farther away than anyone had imagined, but it was also vastly larger than Earth itself. This suggested something almost unthinkable at the time, that we might not be at the center of a cozy, human-scaled cosmos, but rather occupying a small world orbiting a distant, giant star. The implications terrified even Aristarchus. If the sun was so massive and distant, what did that say about those other points of light scattered across the night sky? Could they too be suns, perhaps even more distant than our own? The universe suddenly became not just larger, but potentially incomprehensibly vast. It would take nearly 2,000 years for humanity to fully embrace this cosmic revolution, but the seed of our modern understanding had been planted in that moment of mathematical insight. Fast forward to 1609, when Galileo first turned his primitive telescope toward the heavens. What he saw through that simple arrangement of lenses shattered every comfortable assumption about cosmic scale. The moon revealed itself not as a smooth, perfect sphere, but as a world of mountains and craters, implying it was a place rather than merely a light. Jupiter showed 4 tiny companions dancing around it, proving that not everything in the heavens orbited Earth. Most shocking of all, the Milky Way, that cloudy band of light stretching across the night sky, resolved into countless individual stars. Each of those stars represented a sun potentially like our own. The universe had just expanded from containing perhaps a few thousand visible stars to harbouring multitudes beyond human counting. Yet even Galileo couldn't have imagined the true implications of what he was seeing. Those weren't just more stars, they were glimpses of infinity itself, peeking through the limitations of his primitive instruments. The next great leap came in the 1920s when Edwin Hubble, working with the newly completed Mount Wilson Observatory, made a discovery that would revolutionize our understanding of existence itself. Using the most powerful telescope of his era, Hubble identified what he initially thought were simply nebulous clouds within our own galaxy. But careful observation revealed something extraordinary. These weren't clouds at all, but entire galaxies, island universes containing billions of stars scattered throughout space at distances so vast they had challenged human comprehension. The Andromeda Galaxy, our nearest major galactic neighbour, lay over 2 million light-years away. This meant the light reaching Hubble's telescope had been travelling through space for over 2 million years before arriving at Earth. He wasn't just seeing distant objects, he was seeing ancient history, glimpses of cosmic events that occurred when Earth was inhabited only by primitive life forms. The universe had suddenly become not just unimaginably vast in space, but also in time. But Hubble's most disturbing discovery was yet to come. When he carefully analysed the light from these distant galaxies, he found something that defied all expectations. The galaxies weren't simply scattered randomly through static space. They were all moving away from us. More precisely, the more distant a galaxy was, the faster it appeared to be receding. This suggested something almost impossible to accept. The universe itself was expanding, growing larger with each passing moment. This expansion wasn't like an explosion where objects fly apart through empty space. Space itself was stretching, carrying galaxies along with it like dots painted on an inflating balloon. The implications were staggering. If the universe was currently expanding, then in the past it must have been smaller, denser, hotter. Following this logic backward through time led to a moment when all of existence was compressed into an infinitesimally small point of infinite density and temperature. The Big Bang wasn't just the beginning of matter and energy, it was the beginning of space and time themselves. This brings us to one of the most crucial concepts for understanding cosmic scale, the difference between the universe and the observable universe. The observable universe represents everything we can theoretically see, limited not by the power of our telescopes, but by the fundamental constraint of light speed and cosmic age. Light travels at approximately 186,000 miles per second, but even at this incredible velocity, it takes time to cross cosmic distances. The light from the most distant galaxies we can observe has been travelling toward us for nearly the entire 13.8 billion year history of the universe. Here's where things become beautifully complex. You might expect the observable universe to have a radius of 13.8 billion light-years, since that's how long light has had to reach us. But cosmic expansion complicates this calculation in fascinating ways. While light from the most distant observable objects has indeed been travelling for 13.8 billion years, the objects that emitted that light have been carried much farther away by the expansion of space during the intervening time. When we account for this expansion, the observable universe reveals itself to be a sphere approximately 93 billion light-years in diameter. This represents the absolute limit of what we can ever hope to observe, not because of technological limitations, but because of the fundamental physics of light travel and cosmic expansion. Beyond this cosmic horizon lies mystery absolute, regions of space whose light has not yet had time to reach us, and may never reach us due to accelerating expansion. The scale of even this observable portion defies human intuition. Consider that our entire solar system, from the Sun to the orbit of Neptune, spans roughly 60 astronomical units, where 1 astronomical unit equals the distance from Earth to the Sun. This seems vast until you realise that the nearest star, Proxima Centauri, lies over 250,000 astronomical units away. Our entire solar system would appear as less than a pinprick from that distance. Scale up further, and our Milky Way galaxy contains between 200 and 400 billion stars spread across a disk roughly 100,000 light-years in diameter. If you could somehow shrink the Milky Way to the size of North America, our solar system would be smaller than a coin, and Earth would be invisible to the naked eye. Yet our galaxy represents just one among an estimated 2 trillion galaxies scattered throughout the observable universe. These numbers quickly become meaningless to human cognition. 2 trillion galaxies, each containing hundreds of billions of stars, spread across a sphere 93 billion light-years wide. The total number of stars in the observable universe exceeds the number of grains of sand on every beach and in every desert on Earth. Yet even this incomprehensible multitude represents only what we can see, a tiny fraction of what likely exists beyond our cosmic horizon. Recent statistical analyses of cosmic geometry suggest the true universe extends far beyond our observational limits. The most conservative estimates indicate the entire universe is at least 250 times larger than what we can observe, stretching across roughly 7 trillion light-years. This means for every galaxy we can see in our cosmic neighborhood, there are at least 15 million others scattered through regions of space we'll never observe. Other theoretical models, based on cosmic inflation theory, suggest even more staggering possibilities. If the universe underwent the rapid exponential expansion that most cosmologists believe occurred in its first fraction of a second, the total cosmos could be at least 10 to the 23rd power times larger than our observable portion. This would make the true universe so vast that our observable region, containing trillions of galaxies, would represent less than a single atom within the true cosmic whole. The method by which astronomers measure these cosmic distances represents one of humanity's greatest intellectual achievements. The process begins with what astronomers call the cosmic distance ladder, a series of increasingly sophisticated measurement techniques that allow us to gauge distances across ever greater scales. For nearby objects within our solar system, we can use direct radar measurements or geometric parallax, observing how objects appear to shift position as Earth orbits the Sun. For more distant stars within our galaxy, astronomers employ standard candles, objects whose intrinsic brightness is known, allowing distance calculations based on how dim they appear from Earth. The most important of these standard candles are Type 1a supernovas, stellar explosions that occur when white dwarf stars accumulate matter from companion stars and explode with remarkably consistent peak brightness. Because these explosions always reach roughly the same luminosity, astronomers can determine their distance by measuring how bright they appear from Earth. Dimmer supernovas are farther away, brighter ones are closer. For the most distant objects, astronomers rely on redshift measurements, analysing how the expansion of space stretches light waves as they travel across cosmic distances. This cosmic redshift provides both distance information and evidence for universal expansion. Light from distant galaxies is shifted toward longer, redder wavelengths in proportion to how much space has expanded during the light's journey to Earth. The cosmic microwave background radiation provides another crucial measurement tool. This ancient light, released when the universe first became transparent, roughly 380,000 years after the Big Bang, carries information about cosmic geometry and composition. Tiny temperature fluctuations in this radiation reveal the density variations that eventually grew into galaxies and larger structures, providing a fossil record of the early universe's conditions. Through these sophisticated measurement techniques, astronomers have constructed a detailed model of cosmic evolution and structure. The universe began in an incredibly hot, dense state, and has been expanding and cooling ever since. Initially, this expansion was decelerating due to the gravitational attraction of matter within the cosmos. But observations of distant supernovas in the 1990s revealed something unexpected. The expansion is actually accelerating. This acceleration implies the existence of a mysterious component called dark energy, which appears to comprise roughly 68% of the universe's total mass energy content. Dark energy behaves like a repulsive force, pushing space apart and overwhelming the attractive influence of gravity on large scales. Its nature remains one of the greatest mysteries in modern physics, but its effects are unmistakable in observations of cosmic expansion. Dark matter represents another puzzle, comprising about 27% of cosmic mass energy while remaining invisible to electromagnetic radiation. We know dark matter exists because of its gravitational effects on visible matter, but its composition remains unknown. Together, dark matter and dark energy account for 95% of the universe, meaning everything we can see and touch represents less than 5% of cosmic reality. These invisible components play crucial roles in shaping cosmic structure. Dark matter provides the gravitational scaffolding upon which galaxies and larger structures form, while dark energy determines the universe's ultimate fate by driving accelerated expansion. Understanding their nature and behavior is essential for comprehending how the universe evolved from nearly perfect smoothness in its early moments to the rich tapestry of structure we observe today. The observable universe reveals a cosmos organized on multiple scales, from individual galaxies to vast superclusters connected by filaments of matter spanning hundreds of millions of light-years. Between these structures lie cosmic voids, regions nearly empty of galaxies that can stretch across 300 million light-years of space. This cosmic web of matter and emptiness represents the largest scale organization visible in nature, a pattern that emerged from tiny quantum fluctuations in the early universe. Our Milky Way galaxy occupies a relatively modest position within this cosmic hierarchy. We're part of the Local Group, a small cluster containing about 80 galaxies dominated by the Milky Way, Andromeda, and Triangulum galaxies. The Local Group itself is a minor member of the much larger Virgo supercluster, which contains thousands of galaxies spread across roughly 110 million light-years. Even the Virgo supercluster proves to be just one component of an even larger structure called the Laniakea supercluster, containing over 100,000 galaxies across 520 million light-years. Recent discoveries suggest these superclusters may themselves be organized into even larger patterns, though the limits of observation make such structures difficult to map with certainty. The philosophical implications of these scales challenge every assumption about humanity's cosmic significance. We exist on a small rocky planet orbiting an ordinary star in the outer regions of a typical spiral galaxy, itself a minor member of a modest galaxy group within an unremarkable region of space. Our entire recorded history represents less than a millionth of cosmic time, and our planet occupies less than a trillionth of observable space. Yet paradoxically, this cosmic insignificance may represent our greatest achievement. Through careful observation and brilliant reasoning, a species confined to a tiny world has managed to map the universe across dozens of orders of magnitude, from subatomic particles to cosmic horizons. We've discovered the age and composition of the cosmos, traced its evolution from the first moments to the present, and glimpsed its possible futures. This journey of discovery continues accelerating as new technologies reveal ever deeper cosmic mysteries. Space telescopes like Hubble and the James Webb Space Telescope push our observational horizons toward the edge of the observable universe, while ground-based facilities map the cosmic web in unprecedented detail. Each new observation raises as many questions as it answers, reminding us that the universe's capacity for surprise appears as boundless as its scale. As we stand on the threshold of even greater discoveries, we're left to contemplate what it means to be conscious beings in a cosmos of such magnificent vastness. The The universe may be unimaginably large, but it has given rise to minds capable of contemplating infinity itself. In us, the cosmos has developed the ability to wonder at its own existence, to measure its own dimensions, and to ponder its own meaning. So, the question of cosmic scale ultimately becomes a mirror reflecting our own nature back to us. We are simultaneously insignificant specks of matter, and the universe's method of understanding itself, temporary arrangements of atoms that have learned to contemplate eternity. In seeking to measure the cosmos, we discover not just how big the universe is, but how remarkable it is that anything exists to ask such questions at all. The numbers become even more staggering when we consider what lies beyond our cosmic horizon. That sphere of observation, vast as it seems at 93 billion light-years across, may represent nothing more than a droplet in an infinite ocean of existence. Recent analysis of the cosmic microwave background radiation suggests that space curves so gently, if at all, that it could extend forever in all directions. The geometry of the universe appears remarkably flat, and in mathematics, flat surfaces can stretch to infinity. Think about what this means for a moment. If the universe is truly infinite, then somewhere beyond our cosmic horizon, there exist regions of space identical to our own. The laws of probability in infinite space demand that every possible arrangement of matter must occur not once, but infinitely many times. There could be countless exact copies of Earth, countless versions of you listening to these words, scattered across the infinite expanse like variations on an eternal theme. But even if the universe isn't infinite, the conservative estimates are mind-numbing in their implications. When astronomers analyze the subtle patterns in that ancient cosmic microwave background, they find hints that the true universe extends at least 250 times beyond what we can observe. This means our observable universe, containing its 2 trillion galaxies, represents less than 1 part in 15 million of total reality. The complete cosmos would span roughly 7 trillion light-years, making our entire observable region seem like a grain of sand on an endless beach. Yet even this conservative estimate pales beside the possibilities suggested by cosmic inflation theory. If the universe underwent that brief period of exponential expansion in its first moments, stretching from smaller than a proton to grapefruit size in less time than it takes light to cross an atomic nucleus, then the total cosmos could be incomprehensibly larger still. Some calculations suggest the true universe might be 10 to the 23rd power times larger than what we can see. In this scenario, our observable universe would be to the total cosmos as a single atom is to a sphere the size of Earth's orbit around the Sun. These scales challenge not just our imagination, but the very language we use to describe reality. When we say the universe might be infinite, we're not just talking about something very large. We're contemplating a realm where concepts like edge and beyond lose all meaning. Infinity isn't just a big number. It's a fundamentally different category of existence, where every possible event occurs, where every story gets told, where every moment of wonder and discovery happens not once but countless times across the endless expanse. To navigate this cosmic immensity, astronomers have had to develop increasingly sophisticated tools and techniques. The cosmic distance ladder that allows us to measure these vast scales represents one of humanity's most elegant intellectual achievements. It begins with the familiar, using radar and geometry to map our local solar neighbourhood, then extends through a series of increasingly powerful methods to probe the deepest reaches of space. For nearby stars, astronomers employ parallax, the apparent shift in stellar positions as Earth orbits the Sun. Just as you can gauge the distance to a nearby object by alternately closing each eye and watching it seem to jump back and forth against the background, astronomers measure stellar parallax by observing stars from opposite sides of Earth's orbit. This technique works reliably out to about 1,000 light-years, providing the foundation for all other distance measurements. Beyond parallax range, astronomers turn to standard candles, objects whose intrinsic brightness they understand well enough to use as cosmic lighthouses. Cepheid variable stars, massive stellar giants that pulse with clockwork regularity, serve this purpose beautifully. Their pulsation periods directly correlate with their luminosity, allowing astronomers to determine their distance by comparing how bright they appear from Earth with how bright they actually are. Edwin Hubble used Cepheid variables in nearby galaxies to establish that these spiral nebulae were indeed separate island universes far beyond our own Milky Way. This discovery expanded the known universe by factors of millions overnight, transforming our cosmic perspective from a single galaxy containing everything to a cosmos populated by countless galactic systems. For even greater distances, beyond the reach of individual Cepheid stars, astronomers rely on Type 1a supernovas. These stellar explosions occur when white dwarf stars accumulate matter from companion stars until they reach a critical mass and detonate with tremendous fury. Because this critical mass is always the same, these supernovas reach nearly identical peak brightnesses, making them visible across billions of light years while providing reliable distance indicators. It was observations of distant Type 1a supernovas in the 1990s that revealed the universe's accelerating expansion, leading to the discovery of dark energy. Astronomers expected these distant explosions to appear brighter than they actually did, suggesting they were farther away than predicted by models of a decelerating universe. This dimness could only be explained if cosmic expansion was speeding up rather than slowing down as gravity fought against the initial Big Bang impulse. The most distant objects require redshift analysis, examining how cosmic expansion stretches light waves during their journey across space. As light travels through expanding space, its wavelength gets pulled longer, shifting toward the red end of the spectrum. The amount of redshift directly indicates how much the universe has expanded since the light was emitted, providing both distance and time information for the most ancient observable objects. The cosmic microwave background radiation offers the ultimate standard candle, a nearly uniform glow filling all of space that was emitted when the universe first became transparent, roughly 380,000 years after the Big Bang. This ancient light carries the fossilized imprints of density fluctuations that would eventually grow into galaxies and larger structures. By analyzing the subtle temperature variations in this radiation, astronomers can determine fundamental cosmic parameters, including the universe's age, composition, and geometry. These measurements reveal a cosmos dominated by invisible components whose nature remains mysterious. Dark matter comprises about 27% of the universe's mass energy content, revealing itself only through gravitational effects on visible matter. Galaxy rotation curves show stars orbiting faster than they should, if only visible matter provided the gravitational pull. Gravitational lensing bends light from distant galaxies in patterns that require far more mass than we can see. Computer simulations show that without dark matter's gravitational scaffolding, galaxies and larger structures simply couldn't have formed in the time available since the Big Bang. Dark energy presents an even deeper mystery, comprising roughly 68% of cosmic mass energy, while remaining completely invisible and barely detectable except through its effects on cosmic expansion. Unlike matter, which becomes more dilute as space expands, dark energy maintains constant density throughout the growing universe. This strange property allows it to dominate cosmic evolution despite being incredibly tenuous, perhaps equivalent to just a few hydrogen atoms per cubic meter of space. The competition between dark matter's gravitational attraction and dark energy's repulsive effect determines the universe's ultimate fate. Currently, dark energy is winning, driving accelerated expansion that will eventually carry distant galaxies beyond our observable horizon. In the far future, this acceleration will leave our local group of galaxies isolated in an expanding sea of darkness, as all other cosmic structures disappear beyond our ability to observe them. Within this vast cosmic arena, matter organizes itself into a magnificent hierarchy of structures spanning dozens of orders of magnitude in scale. At the smallest level, quantum fluctuations in the early universe provided the seeds for all subsequent organization. These tiny density variations, preserved in the cosmic microwave background, grew under gravity's influence into the cosmic web we observe today. This web consists of dense filaments of matter stretching across hundreds of millions of light years, connected at intersections where massive galaxy clusters form. Between these filaments lie vast cosmic voids, regions nearly empty of galaxies that can span 300 million light-years of space. The filaments themselves contain over half of all ordinary matter in the universe, channeling gas and smaller galaxies toward the dense nodes where major galaxy clusters continue growing through mergers and accretion. The largest known structure in this cosmic web is the Hercules corona borealis Great Wall, a collection of galaxy clusters stretching across 10 billion light-years. This structure is so vast it challenges our theoretical understanding of how such massive organizations could have formed in the time available since the Big Bang. Its existence suggests that either our models of structure formation need revision, or that we're seeing statistical fluctuations in the cosmic matter distribution, rather than genuine connected structure. Our Milky Way galaxy occupies a modest position within this hierarchy. Containing perhaps 400 billion stars spread across a disk 100,000 light-years in diameter, it ranks as a large spiral galaxy, but nothing exceptional by cosmic standards. We're part of the Local Group, a small collection of about 80 galaxies dominated by the Milky Way, Andromeda, and Triangulum systems. The entire Local Group spans roughly 10 million light-years and contains perhaps 1 trillion stars total. The Local Group itself belongs to the Virgo supercluster, a collection of thousands of galaxies spread across 110 million light-years. But even this vast assemblage proves to be just one component of the much larger Laniakea supercluster, containing over 100,000 galaxies across 520 million light-years. Recent mapping suggests these superclusters may themselves be organized into even larger patterns, though the limits of observation make such ultra-large-scale structures difficult to study reliably. At each level of this hierarchy, the same fundamental forces operate according to the same physical laws, yet the phenomena that emerge become increasingly complex and beautiful. Stars form from gravitational collapse of gas clouds, but their nuclear fusion creates heavy elements that enable rocky planet formation. Galaxies grow through mergers and gas accretion, but their spiral arms and central black holes create environments where star formation can proceed efficiently across billions of years. Galaxy clusters provide the gravitational wells where galaxies can interact and evolve, but their hot gas atmospheres and dark matter halos create unique physical conditions found nowhere else in nature. The philosophical weight of these scales becomes overwhelming when we try to place human experience within this cosmic context. Our entire species has existed for less than 1 million years, a fleeting instant compared to the 13.8 billion year age of the universe. Our recorded history spans perhaps 5,000 years, representing less than 1/1,000,000th of cosmic time. An individual human lifetime of 80 years corresponds to roughly 6 trillionths of the universe's age. The Sun's diameter is about 1.4 million kilometers. In our solar system, comparatively, the proportions are even more humbling. Earth's diameter of 12,800 kilometers seems substantial, until you compare it to the Sun. The solar system itself stretches about 4.5 billion kilometers from the Sun to Neptune's orbit. Yet even this vast span shrinks to insignificance against the 4.2 trillion kilometers separating us from the nearest star. The Milky Way's 100,000 light-year diameter dwarfs our solar system by factors of billions, yet our galaxy is just one among trillions scattered across the observable universe. If we could somehow shrink the observable universe to the size of Earth, our entire galaxy would be smaller than a grain of sand. Our solar system would be invisible to the most powerful microscope, and Earth itself would be utterly undetectable by any conceivable measurement technique. The entire history of human civilization would have occurred within a volume smaller than a single atom in this scaled-down cosmos. Yet this cosmic insignificance contains within it the seeds of profound meaning. Somehow, within this vast universe of mostly empty space and dark matter, conditions arose that allowed stars to forge heavy elements, planets to form from stellar debris, and life to emerge from complex chemistry. Against astronomical odds, the universe gave rise to consciousness capable of contemplating its own existence, measuring its own dimensions, and wondering at its own magnificent complexity. We are not separate from this cosmic story, but integral participants in it. The calcium in our bones was forged in stellar cores. The iron in our blood was created in supernova explosions. The oxygen we breathe was manufactured in massive stars that lived and died billions of years before Earth formed. We are not merely observers of the cosmos, but expressions of it, temporary arrangements of stellar debris that have learned to ponder infinity. In us, the universe has developed the capacity to know itself, to measure its own vastness, and to ask questions about its own meaning and purpose. We may be infinitesimally small compared to cosmic scales, but we represent something unprecedented in the known universe. Matter organized in such a way that it can contemplate matter, space that can ponder space, time that can wonder about time. This perspective transforms our understanding of what it means to be human in an age of cosmic awareness. We are simultaneously the most insignificant of dust motes and the most remarkable achievement in the observable universe. Our smallness is not a diminishment, but an amplification of wonder. How extraordinary that anything should exist at all, let alone conscious beings capable of discovering their place within the infinite tapestry of existence. As our instruments continue pushing deeper into space and further back in time, we're reminded that every answer reveals new mysteries, every measurement opens new questions, every discovery expands rather than limits the scope of cosmic wonder. The universe appears to be not only stranger than we imagine, but stranger than we can imagine, filled with phenomena and possibilities that stretch the limits of human comprehension. Perhaps that's the most profound insight emerging from our exploration of cosmic scale. The universe is not only vast beyond measure, but inexhaustible in its capacity to surprise, challenge, and inspire those rare arrangements of matter fortunate enough to contemplate their cosmic home. In seeking to measure infinity, we discover not our limitations but our extraordinary privilege as conscious participants in the greatest story ever told. The more we peer into the depths of space, the more we realize we're looking at a universe that seems designed to humble human ambition. Every time we think we've grasped the full scope of existence, another discovery arrives to shatter our cosmic confidence once again. The James Webb Space Telescope, humanity's most sophisticated eye on the universe, has recently captured images of galaxies so distant their light began its journey when the cosmos was barely 400 million years old. These aren't just pretty pictures, they're time machines showing us a universe in its cosmic infancy, already teeming with massive galaxies that shouldn't exist according to our best theories. What we're seeing challenges everything we thought we knew about cosmic evolution. These ancient galaxies appear surprisingly mature and massive for their age, suggesting that structure formation in the early universe proceeded far more rapidly than our models predicted. It's like finding a fully grown oak tree in what you expected to be a field of seedlings. Each observation forces us to revise our understanding, not just of how big the universe is, but of how quickly it learned to organize itself into the magnificent structures we observe today. Consider the galaxy cluster Abell 2744, nicknamed Pandora's cluster because opening our eyes to its true nature unleashed a cascade of cosmic mysteries. This gravitational monster contains the mass of 4 trillion suns spread across several million light-years of space. But here's what makes it truly extraordinary. The cluster acts as a natural telescope, its immense gravitational field bending and magnifying light from even more distant galaxies behind it. Through this cosmic lens, we can observe objects that would otherwise remain forever beyond our reach. The galaxies we see through Abell 2744's gravitational lensing appear as they were over 13 billion years ago, when the universe was less than 1 billion years old. Some of these ancient light sources may represent the very first generation of galaxies, cosmic pioneers that began the long process of transforming the universe from a dark, featureless expanse into the rich tapestry of structure we inhabit today. Yet even these primordial beacons represent just the beginning of the story, hints of vast cosmic regions that extend far beyond anything we can directly observe. The cosmic web that connects all these structures reveals itself as perhaps the most elegant pattern in nature. Imagine a 3-dimensional spider web stretching across billions of light years, with galaxies strung along its filaments, like dewdrops on silk threads. These cosmic highways channel matter across the universe, feeding the growth of galaxy clusters at their intersections while leaving vast empty spaces between the strands. The Sloan Great Wall, one of the largest known structures, stretches 1.4 billion light-years across, containing hundreds of thousands of galaxies arranged in sheets and filaments of breathtaking complexity. Within this cosmic architecture, our local supercluster of galaxies appears almost quaint in its modest proportions. The Virgo cluster, our gravitational destination, as the local group falls toward its massive embrace, contains over 1,300 member galaxies spread across 15 million light-years. At its heart lies the giant elliptical galaxy, M87, harbouring a supermassive black hole 6.5 billion times more massive than our Sun. This cosmic monster was the first black hole ever photographed. Its event horizon, shadow appearing as a dark circle surrounded by the brilliant glow of matter spiralling to its doom. Yet even M87's supermassive black hole shrinks to insignificance when compared to some of the universe's true giants. The black hole at the centre of the galaxy, Phoenix A, weighs in at roughly 100 billion solar masses, making it one of the most massive objects known to exist. Its event horizon would encompass an area larger than our entire solar system, and its gravitational influence shapes the evolution of its host galaxy across cosmic time. The mere existence of such objects challenges our understanding of how black holes grow and merge in the early universe. These extreme objects serve as natural laboratories for testing the fundamental laws of physics under conditions we could never hope to recreate on Earth. Near the event horizon of a massive black hole, space and time becomes so warped that minutes for a nearby observer could correspond to hours for someone watching from a safe distance. The gravity is so intense that it literally stretches the fabric of space-time, creating regions where our normal concepts of causality and temporal sequence break down entirely. Einstein's general relativity predicts these exotic phenomena with mathematical precision, but experiencing them remains beyond human capability. We can only observe their effects from afar, watching as matter accelerates to significant fractions of light speed before disappearing forever beyond the event horizon. The energy released by this process powers some of the brightest objects in the universe, quasars that can outshine entire galaxies and remain visible across billions of light-years of space. The supermassive black holes that power these brilliant beacons may themselves be products of the universe's earliest epochs. Primordial black holes, formed from density fluctuations in the first moments after the Big Bang, could have provided the seeds around which the first galaxies assembled. These ancient gravitational anchors may have guided cosmic evolution from the very beginning, determining where and how the first stars would form, and shaping the large-scale structure we observe today. As we trace cosmic evolution backward through time, we encounter epochs when the universe bore no resemblance to its current state. The cosmic dark ages, lasting from roughly 380,000 years to several hundred million years after the Big Bang, represent a time when no stars had yet formed to illuminate the expanding cosmos. The universe was filled with neutral hydrogen and helium gas, slowly cooling as space expanded, waiting for gravity to collect enough matter to ignite the first nuclear furnaces. When those first stars finally blazed to life, they transformed the universe forever. These primordial giants, perhaps hundreds of times more massive than our Sun, burned through their nuclear fuel in just a few million years before exploding as the first supernovas. Their deaths scattered heavy elements throughout space for the first time, providing the raw materials necessary for rocky planets and complex chemistry. Without these stellar pioneers, the universe would have remained a cold, dark realm of hydrogen and helium, incapable of supporting the rich diversity of matter and energy we observe today. The transition from this primordial simplicity to modern complexity represents one of the most remarkable transformations in cosmic history. From a nearly uniform sea of elementary particles, the universe has evolved into a magnificent hierarchy of organization spanning scales from subatomic to cosmic. Quarks combine into protons and neutrons, which form atomic nuclei that capture electrons to create atoms. Atoms bind into molecules, which assemble into complex chemistry, which enables the emergence of life and ultimately consciousness itself. Each level of this hierarchy operates according to the same fundamental physical laws, yet displays emergent properties that cannot be predicted from the behavior of its components alone. The quantum mechanics that governs subatomic particles gives no hint of the classical physics that describes planetary orbits. The gravitational dynamics of galaxy clusters reveals nothing about the biochemistry that enables living organisms to process information and respond to their environments. This emergence of complexity from simplicity represents perhaps the universe's most profound achievement. Against the relentless tendency toward thermal equilibrium and maximum entropy, local regions of space have organized themselves into structures of stunning sophistication and beauty. Stars maintain their nuclear fires for billions of years. Planets develop stable climates that persist across geological ages, and living systems evolve increasing levels of organization and capability over time. The anthropic principle suggests that this progression toward complexity may not be accidental. In a universe with slightly different physical constants, stars might never form, or they might burn out too quickly to allow planetary development. The nuclear forces that bind atomic nuclei must be precisely tuned to allow both hydrogen fusion in stellar cores and the formation of heavier elements through successive nuclear reactions. The strength of gravity must be exactly right to allow galaxy formation without causing immediate cosmic collapse. These remarkable coincidences have led some scientists to propose that our universe may be just one member of an infinite multiverse, where every possible combination of physical constants plays out in separate cosmic domains. In this scenario, we observe a universe fine-tuned for complexity and consciousness, not because it was designed that way, but because we could only exist in a universe with precisely these properties. The vast majority of possible universes would remain dark and lifeless, while a tiny fraction, like our own, would develop the conditions necessary for awareness to emerge. Whether or not the multiverse hypothesis proves correct, the fine-tuning problem highlights just how special our cosmic circumstances appear to be. The universe seems almost implausibly well-suited for the development of complexity, consciousness, and scientific understanding. Stars live long enough for planets to form and life to evolve. Heavy elements exist in sufficient abundance to enable rocky world formation. The cosmic expansion rate allows enough time for galaxy formation without preventing the development of stable stellar systems. These favourable conditions may be temporary features of our cosmic epoch. In the distant future, as dark energy drives accelerated expansion, star formation will gradually cease as gas becomes too diffuse to collapse under gravity. Existing stars will slowly exhaust their nuclear fuel, leaving behind white dwarfs, neutron stars, and black holes as the only remaining compact objects. The universe will enter a long twilight phase where energy becomes increasingly difficult to extract and entropy steadily increases. Eventually, even protons may decay, dissolving atomic nuclei and reducing all matter to elementary particles and radiation. Black holes will slowly evaporate through Hawking radiation, taking trillions upon trillions of years to disappear completely. The final state of the universe may be a cold, dark expanse populated only by photons and elementary particles, forever expanding and cooling toward absolute zero temperature. Yet even this far future scenario contains elements of wonder and mystery. The quantum vacuum itself may prove unstable over these vast timescales, potentially giving birth to new forms of organization we cannot currently imagine. Virtual particle fluctuations might occasionally produce matter and energy, creating brief islands of complexity in the cosmic desert. The laws of physics themselves might evolve, opening possibilities for phenomena that remain forever beyond our current understanding. These speculations remind us that, despite centuries of scientific progress, we remain cosmic infants in our understanding of reality's full scope and nature. Every answer we discover reveals new questions. Every solved mystery opens doors to greater mysteries still. The universe appears to be not only larger than we imagine, but more strange and wonderful than we have yet learned to imagine. Our position as conscious observers of this magnificent cosmic drama remains one of its most remarkable features. Through us, the universe has developed the ability to study itself, to measure its own dimensions, and to ponder its own meaning and purpose. We are not separate from the cosmic story, but integral expressions of it, temporary arrangements of stellar debris that have learned to contemplate infinity and find it beautiful. In these quiet moments when we pause to consider our place within the vast cosmic web, we touch something profound about the accidents and the most remarkable achievement in the observable nature of existence itself. We are simultaneously the most insignificant of cosmic universe. Our smallness is not a limitation but an amplification of wonder, reminding us how extraordinary it is that anything exists at all, let alone conscious beings capable of discovering their cosmic heritage. The numbers that describe cosmic scale will continue growing as our instruments peer deeper into space and further back in time. New telescopes will reveal ever more distant galaxies, more ancient light, more extreme phenomena that challenge our theoretical understanding. But perhaps the most important discovery we've already made is that we live in a universe magnificent enough to deserve our attention, complex enough to reward our curiosity, and beautiful enough to inspire our deepest sense of wonder. As you drift off to sleep tonight, remember that you're traveling through this cosmic immensity at tremendous speed, carried along by Earth's rotation, our planet's orbit, the sun's motion through the galaxy, and the galaxy's journey through expanding space. You're part of the universe's ongoing experiment in consciousness and complexity, a temporary arrangement of ancient stardust that has learned to ponder its own cosmic significance. The universe may be unimaginably vast, but it has given rise to minds capable of contemplating that vastness and finding meaning within it. In seeking to measure the cosmos, we discover not just how big it is, but how remarkable we are for being able to ask such questions at all. Sweet dreams, fellow travelers, through the infinite expanse of space and time. Yet even as we contemplate these mind-bending scales, we're only beginning to grasp the true magnitude of our cosmic predicament. The observable universe, vast as it seems with its 93 billion light-year diameter and 2 trillion galaxies, may represent nothing more than a cosmic droplet in an ocean so immense that our most ambitious measurements become meaningless whispers in the face of infinity itself. Picture this unsettling truth. Right now, beyond the farthest reaches of what our most powerful telescopes can detect, there exist regions of space so distant that their light will never reach us. Not because our instruments lack sensitivity, but because the very fabric of space itself is expanding faster than light can traverse it. We are prisoners of our cosmic horizon, forever cut off from vast realms of existence that lie tantalizingly beyond our observational reach. This cosmic censorship operates through the same mechanism that gives our observable universe its finite size. While light from the cosmic microwave background has been traveling toward us for 13.8 billion years, the regions that emitted that ancient radiation have been carried much farther away by cosmic expansion. It's like trying to catch up with someone walking away from you on a moving walkway that's accelerating faster than you can run. No matter how fast you move, the distance between you keeps growing. The implications become truly staggering when we consider what this means for the universe beyond our cosmic horizon. Recent analysis of the cosmic microwave background's subtle patterns suggests that space extends far beyond what we can observe, potentially stretching across distances that dwarf our observable region by incomprehensible factors. The most conservative estimates indicate the true universe spans at least 7 trillion light-years, making our observable cosmos seem like a grain of sand on an endless beach. But even this conservative figure fails to capture the full scope of cosmic possibility. When cosmologists trace the implications of cosmic inflation theory backward through time, they encounter scenarios where the true universe could be vastly larger still. If that brief period of exponential expansion in the universe's first fraction of a second stretch space by the factors their equations suggest, then our observable region might represent less than 1 part in 10 to the 23rd power of total reality. Try to wrap your mind around this proportion. If the true universe is 10 to the 23rd power times larger than what we can observe, then our entire observable cosmos, with its 2 trillion galaxies and 93 billion light-year diameter, would be to the total universe as a single atom is to a sphere the size of Earth's orbit around the Sun. Every star we've ever catalogued, every galaxy we've ever photographed, every cosmic structure we've ever mapped would constitute less than a subatomic speck within the true cosmic whole. These numbers transcend human comprehension so completely that they challenge the very meaning of existence itself. In an infinite or near-infinite universe, the laws of probability demand that every possible arrangement of matter must occur not once, but countless times. Somewhere beyond our cosmic horizon, there exist perfect copies of our Milky Way galaxy, identical down to the last hydrogen atom. There are countless versions of Earth, countless versions of human civilization, countless versions of you listening to these words at this very moment. The mathematics of infinity are merciless in their implications. If space stretches forever, then everything that can happen will happen, and it will happen an infinite number of times. Every possible variation of your life plays out somewhere in the cosmic expanse. Every book that could be written, every song that could be composed, every thought that could be thought exists in infinite repetition across the boundless reaches of space. This possibility transforms our understanding of uniqueness and significance in ways that are both humbling and profound. Your life, precious and irreplaceable as it feels to you, might be one of infinitely many identical lives being lived simultaneously across the cosmos. Yet paradoxically, this doesn't diminish your importance. Even in an infinite multiverse of possibilities, your consciousness remains the only one you'll ever experience, making your perspective on existence absolutely unique and irreplaceably valuable. The techniques astronomers use to probe these cosmic depths represents some of humanity's most ingenious achievements in measurement and deduction. When Edwin Hubble first observed that distant galaxies appeared redder than nearby ones, he was witnessing the stretching of space itself as light waves rode the expanding fabric of reality across billions of years. This cosmic redshift provides our most powerful tool for measuring distances to the edge of the observable universe. As light travels through expanding space, its wavelength gets stretched proportionally to how much the universe has grown during its journey. Light from galaxies we observe, as they were 10 billion years ago, shows redshift values that tell us exactly how much space has expanded since that light began its voyage to Earth. By combining these redshift measurements with our understanding of cosmic expansion history, astronomers can trace the evolution of the universe from its earliest observable moments to the present day. The cosmic microwave background radiation offers our deepest glimpse into this ancient past, carrying information from when the universe was only 380,000 years old and had just become transparent to light for the first time. This primordial glow fills all of space with nearly perfect uniformity, yet contains tiny temperature fluctuations that map the density variations from which all cosmic structure eventually grew. These fluctuations, measured to precisions of microkelvin, reveal the quantum mechanical seeds that inflation stretched across cosmic scales in the universe's first moments. Regions that were slightly denser than average eventually collapsed under their own gravity to form the first stars and galaxies, while slightly less dense regions became the cosmic voids that separate galactic structures today. The patterns preserved in this ancient light provide our most detailed map of the early universe's conditions, and our strongest evidence for the inflationary epoch that may have created the vast cosmos we inhabit. Modern space telescopes push these measurements to their absolute limits, detecting galaxies so distant that we observe them as they existed when the universe was less than 5% of its current age. The James Webb Space Telescope has recently captured light from galaxies that formed when the cosmos was barely 400 million years old, revealing surprisingly mature stellar systems that challenge our understanding of early cosmic evolution. These observations suggest that galaxy formation proceeded much more rapidly in the early universe than theoretical models predicted, implying that the first stars may have been more massive and shorter-lived than previously thought. Each new discovery forces astronomers to revise their understanding of how quickly the universe transformed from its initially smooth state into the rich tapestry of structure we observe today. Yet for all our observational prowess, we remain fundamentally limited by the physics of light travel and cosmic expansion. There exists an absolute horizon beyond which no information can ever reach us, not because of technological limitations, but because of the finite speed of light and the accelerating expansion of space itself. This cosmic event horizon moves outward at roughly 1 light-year per year, gradually bringing new regions of space within our observable range, while simultaneously pushing the most distant observable objects closer to the edge of detection. The dark energy driving this acceleration remains one of the deepest mysteries in modern physics. Comprising roughly 68% of the universe's total mass energy content, this invisible component behaves like a repulsive force that grows stronger as space expands. Unlike matter, which becomes more dilute as the universe grows, dark energy maintains constant density throughout the expanding cosmos, providing an ever-increasing push that overcomes the attractive pull of gravity on large scales. Einstein's cosmological constant offers the simplest explanation for dark energy, suggesting that empty space itself possesses inherent energy that drives cosmic expansion. According to this model, the vacuum of space contains a small, but non-zero energy density that translates into a repulsive gravitational effect. As the universe expands and more space comes into existence, more of this vacuum energy appears, providing an ever stronger push that accelerates the expansion. Alternative theories propose more exotic explanations, including scalar fields that vary across space and time, modifications to Einstein's general relativity on cosmic scales, or interactions between our universe and parallel dimensions in a higher dimensional multiverse. Each possibility carries profound implications for the ultimate fate of cosmic evolution and the nature of reality itself. The competition between dark energy's repulsive effect and gravity's attractive influence will determine whether the universe expands forever, reaches a maximum size and contracts, or undergoes more complex evolutionary cycles. Current observations strongly favour eternal expansion, suggesting that dark energy will eventually overcome all gravitational bonds and leave our local group of galaxies isolated in an ever-expanding sea of darkness. This cosmic loneliness awaits us in the far future as accelerating expansion carries distant galaxies beyond our observable horizon. Stars that we can see today will eventually disappear from view as their light can no longer overcome the stretching of space between us. Future astronomers, if any exist, will inherit a much smaller observable universe, containing only the gravitationally bound structures in our immediate cosmic neighbourhood. The cosmic web that currently connects galaxies across billions of light years will gradually fade from view as its constituent structures recede beyond the reach of light itself. The magnificent filaments and walls that trace the largest patterns in nature will become invisible, leaving future observers with a much more limited perspective on cosmic architecture. They may never know that the universe once revealed itself as a vast interconnected network of matter and energy spanning unimaginable distances. Within this grand cosmic web, our local supercluster occupies a position that seems almost deliberately modest. The Laniakea supercluster, containing over 100,000 galaxies across 520 million light-years, represents our address in the cosmic hierarchy. Yet even this vast assemblage shrinks to insignificance when viewed against the full scope of observable structure, appearing as little more than a minor node in the universal network of matter and energy. The Milky Way itself, despite containing hundreds of billions of stars and spanning 100,000 light-years, occupies such a tiny fraction of cosmic space that it would be invisible if the observable universe were scaled down to the size of Earth. Our entire galactic home, with all its spiral arms, star-forming regions, and ancient globular clusters, would disappear without a trace in this cosmic reduction, unable to register even as a single pixel in the grandest possible photograph of existence. This perspective transforms every aspect of human experience and achievement. Our species has existed for perhaps 300,000 years, a duration so brief compared to cosmic time that it represents less than 0.002% of the universe's 13.8 billion year history. The entire span of recorded human civilization, from the first written languages to the present day, encompasses roughly 5,000 years, or about 0.000036% of cosmic time. Your individual lifetime represents approximately 6 trillionths of the universe's age. Yet within this infinitesimal time span, humanity has managed to discover its cosmic context with remarkable precision. We've measured the universe's age to within 1% accuracy, mapped its large-scale structure across billions of light years, and traced its evolution from the first moments after the Big Bang to the present day. We've identified the components that dominate cosmic evolution, even though we don't understand their fundamental nature. We've glimpsed the quantum fluctuations that seeded all subsequent structure formation. This achievement represents something genuinely unprecedented in the known universe. Through careful observation, mathematical analysis, and brilliant theoretical insight, a species confined to a single small planet has managed to comprehend its place within a cosmos that extends far beyond direct experience. We've discovered that we are made of elements forged in stellar cores, that we inhabit a galaxy among trillions, that we exist within a universe that may be infinite in extent. The philosophical implications of this cosmic awareness challenge every traditional framework for understanding human significance and purpose. We are simultaneously the most insignificant specks imaginable and the most remarkable achievements we know of in the observable universe. Our physical size and temporal duration are utterly negligible compared to cosmic scales. Yet our capacity for understanding and appreciation appears to be unique among all known phenomena. This paradox of cosmic insignificance and unprecedented capability suggests that consciousness itself may represent the universe's most extraordinary achievement. Against the overwhelming tendency toward thermal equilibrium and maximum entropy, local regions of space have organized themselves into structures capable of contemplating their own existence. Stars maintain their nuclear fires for billions of years. Planets develop stable environments that persist across geological ages, and living systems evolve increasing levels of complexity and awareness over time. The emergence of consciousness from non-living matter remains one of the deepest mysteries in science. Yet it has clearly occurred at least once in our cosmic neighborhood. Through us, the universe has developed the ability to study itself, to measure its own dimensions, and to ponder its own meaning and destiny. We are not separate from the cosmic story, but integral expressions of it, temporary arrangements of stellar debris that have learned to contemplate infinity. In these quiet moments, when we pause to consider our place within the vast cosmic web, we touch something profound about the nature of existence itself. The universe may be unimaginably large, potentially infinite in extent, filled with structures and phenomena that dwarf human comprehension. Yet it has given rise to minds capable of grasping these scales and finding meaning within them. The numbers that describe cosmic immensity will continue growing as our instruments peer deeper into space and further back in time. New telescopes will reveal ever more distant galaxies, more extreme phenomena, more evidence of the universe's magnificent scale and complexity. But perhaps the most important discovery we've already made is that we live in a cosmos worthy of our attention, complex enough to reward our curiosity, and beautiful enough to inspire our deepest sense of wonder. As you contemplate these cosmic scales tonight, remember that you are part of this grand story of structure and evolution. The atoms in your body were forged in stellar cores billions of years ago, scattered through space by supernova explosions, and eventually incorporated into the rocky world where consciousness learned to ponder its own origins. You carry within yourself the chemical legacy of cosmic evolution, a living library of the universe's 13.8 billion year journey from simplicity to complexity. The darkness between the stars is not empty, but filled with invisible matter and energy that shape cosmic evolution on the largest scales. Dark matter provides the gravitational scaffolding upon which galaxies form and evolve, while dark energy drives the accelerating expansion that will determine the universe's ultimate fate. These mysterious components, comprising 95% of cosmic reality, remind us how much we still don't know about the universe we inhabit. Yet our ignorance is not a limitation, but an opportunity. Every unanswered question represents a frontier waiting to be explored, every mystery an invitation to deeper understanding. The universe appears to be not only larger than we imagine, but stranger than we can imagine, filled with phenomena and possibilities that stretch the limits of human comprehension. The cosmic web continues its ancient dance of expansion and evolution, carrying galaxies along vast filaments toward an uncertain future. New stars form in stellar nurseries scattered throughout space, while others exhaust their nuclear fuel and collapse into white dwarfs, neutron stars, or black holes. Galaxies merge and interact, creating new environments where different forms of cosmic chemistry can unfold. Throughout this grand cosmic drama, consciousness remains a rare and precious phenomenon, perhaps unique to our small corner of space, or perhaps scattered across countless worlds throughout the infinite expanse. Either possibility fills us with wonder at our extraordinary circumstances. If we are alone, then consciousness represents an achievement of staggering improbability. If we are not alone, then the universe may be filled with other minds contemplating the same cosmic mysteries that captivate us. The search for extraterrestrial intelligence takes on new meaning when viewed against these cosmic scales. In a universe potentially containing trillions of galaxies, each with hundreds of billions of stars, the statistical arguments for life elsewhere become compelling. Yet the vast distances between stars and galaxies create barriers to communication and contact that may be insurmountable, leaving each conscious species isolated within their own cosmic bubble of awareness. These considerations transform our relationship with the cosmos from one of conquest or exploitation to one of profound respect and careful stewardship. We may be the only conscious observers in our local region of space, making us responsible for preserving and expanding the universe's capacity for self-awareness. Every act of scientific discovery, every moment of cosmic contemplation, every expression of wonder and appreciation contributes to the universe's growing understanding of itself. The scales we've explored tonight represent just the beginning of our cosmic journey. As our instruments become more sensitive and our theories more sophisticated, we'll continue pushing the boundaries of the observable universe, perhaps discovering phenomena that challenge our most fundamental assumptions about the nature of reality. The cosmic horizon that currently limits our observations may prove to be just one of many barriers waiting to be transcended by future generations of cosmic explorers. In the meantime, we remain travelers on a small world orbiting an ordinary star in the outer regions of a typical galaxy, carried along by cosmic expansion toward destinations we'll never reach. Yet through our consciousness and curiosity, we've managed to map our position within the vast cosmic web, measure our journey through space and time, and contemplate the infinite possibilities that surround us. The universe may be unimaginably vast, potentially infinite in extent, filled with structures and phenomena that reduce human experience to cosmic insignificance. But it has given rise to minds capable of comprehending that vastness and finding profound meaning within it. In seeking to measure the cosmos, we discover not just how big it is, but how remarkable we are for being able to ask such questions at all. As cosmic expansion continues carrying distant galaxies beyond our observable horizon, we're reminded that our window on the universe is both precious and temporary. The cosmic microwave background that reveals the universe's ancient conditions will gradually cool and redshift beyond detection. The most distant galaxies we can observe today will eventually disappear from view as their light can no longer overcome the stretching of space. Future astronomers may inherit a much lonelier cosmos, with only the gravitationally bound structures in our local group remaining visible against the cosmic background. They may never know that the universe once revealed itself as a magnificent web of matter and energy extending across unimaginable distances. This makes our current era of cosmic discovery especially precious, a golden age when the universe still reveals its grandest secrets to those patient enough to look and wise enough to understand what they're seeing. The philosophical weight of these discoveries continues to reshape human culture and consciousness in ways we're only beginning to appreciate. We are the first generation in human history to possess detailed knowledge of our cosmic context, to understand our place within the universal hierarchy of structure and scale. This knowledge brings both humility and responsibility, reminding us of our cosmic insignificance while highlighting our unprecedented role as the universe's method of understanding itself. Every night when you look up at the stars, you're peering into the depths of space and time, seeing light that has traveled across vast cosmic distances to reach your eyes. Some of that light began its journey before Earth formed, carrying information about cosmic conditions in the distant past. You are directly connected to the cosmic web through the photons entering your retina, making you an active participant in the universe's ongoing experiment in consciousness and complexity. The darkness between those visible stars is filled with invisible matter and energy that shape cosmic evolution on scales we can barely comprehend. Dark matter halos surround every galaxy, providing the gravitational architecture that allows stellar systems to form and persist across cosmic time. Dark energy permeates all of space, driving the acceleration that will determine whether the universe expands forever or undergoes more complex evolutionary cycles. These mysterious components remind us that the universe we observe directly represents less than 5% of cosmic reality. The remaining 95% consists of phenomena we can detect only through their gravitational effects, leaving vast realms of physics and cosmology waiting to be explored. Future discoveries may reveal that our current understanding of cosmic scale and structure represents just the beginning of an even grander story of existence and evolution. As we reach the end of our cosmic journey tonight, we're left with a profound appreciation for both the vastness of the universe and the remarkable achievement of consciousness within it. The cosmos may extend far beyond our ability to observe or comprehend, filled with structures and phenomena that dwarf human imagination. Yet through careful observation and brilliant reasoning, we've managed to map our place within this infinite expanse and find deep meaning in our cosmic circumstances. You are made of ancient starlight, forged in nuclear furnaces that burned billions of years before Earth existed, scattered through space by stellar explosions, and eventually assembled into the complex arrangements of matter that enable thought and wonder. Your consciousness represents the universe becoming aware of itself, matter learning to contemplate its own existence, space and time developing the capacity to ponder their own nature and purpose. In these quiet moments of cosmic contemplation, you touch something profound about the relationship between mind and universe, between the infinitesimally small and the infinitely large, between the temporary and the eternal. The scales we've explored tonight remind us that we are, simultaneously, most remarkable achievements in the known cosmos, temporary arrangements of atoms, insignificant specks of dust and that have learned to appreciate infinity itself. The universe continues its ancient expansion, carrying galaxies toward distant futures we can only imagine, while consciousness flickers briefly in scattered pockets of organized complexity. Whether we are alone or part of a vast community of thinking beings, we remain privileged witnesses to the greatest story ever told, participants in the cosmos's ongoing journey of discovery and self-understanding. Sweet dreams, fellow travelers through the infinite expanse of space and time. May your rest be filled with visions of cosmic wonder, and your waking hours enriched by the knowledge that you are integral participants in the universe's magnificent experiment in consciousness and complexity. The story of cosmic measurement reaches its most profound chapter when we confront what may be the ultimate truth about our universe. The observable cosmos, vast as it appears with its 93 billion light-year span and 2 trillion galaxies, might represent nothing more than a single raindrop in an infinite ocean of existence. Tonight, as we peer beyond the edge of what we can see, we enter territory where mathematics merges with philosophy and where human comprehension encounters its most humbling limits. Picture yourself standing on a beach at night, watching waves crash against the shore under a star-filled sky. Each wave that reaches your feet has travelled across vast expanses of ocean, carrying energy that began its journey perhaps thousands of miles away. Yet no matter how far you peer into the darkness, you can only see to the horizon, beyond which lies ocean that remains forever hidden from your view. The cosmic horizon works in precisely the same way, but instead of being limited by Earth's curvature, We're constrained by the fundamental properties of light and time themselves. This cosmic horizon doesn't represent a wall or barrier in any physical sense. It's more like a temporal boundary, marking the distance light could have travelled since the universe first became transparent to electromagnetic radiation. Beyond this boundary lies what cosmologists call the unobservable universe, regions of space whose light hasn't had sufficient time to reach us, no matter how powerful our telescopes might become. The mathematics behind this boundary tell a story both beautiful and unsettling. When astronomers trace the expansion of space backward through time, they discover that the cosmic microwave background radiation we observe today was emitted when the universe was merely 380,000 years old. This ancient light has been travelling toward us ever since, but during its journey, the expansion of space has carried the regions that emitted it much farther away. The result is our current observable sphere with its 46.5 billion light-year radius. Yet recent theoretical work suggests this observable region may be almost negligibly small compared to the true extent of cosmic reality. When cosmologists analyze the geometry of space using data from missions like the Planck satellite, they find that the universe appears remarkably flat. In mathematical terms, flat space can extend infinitely in all directions, suggesting that what we observe might be merely a tiny sample of a boundless cosmic expanse. Even the most conservative estimates paint a picture that challenges human comprehension. Statistical analysis of cosmic structure patterns suggests the universe extends at least 250 times beyond our observable horizon. This would place the minimum size of the true cosmos at roughly 7 trillion light-years across, making our observable universe seem like a grain of sand on an endless beach. Every galaxy we've catalogued, every star we've named, every cosmic phenomenon we've discovered would constitute less than 1 part in 15 million of total cosmic reality. But these conservative figures pale beside the possibilities suggested by cosmic inflation theory. If the universe underwent the rapid exponential expansion that most cosmologists believe occurred in its first fleeting moments, the true cosmos could be incomprehensibly larger still. Some calculations suggest the entire universe might be at least 10 to the 23rd power times bigger than what we can observe. In this scenario, our observable cosmos would be to the total universe as a single atom is to a sphere the size of Earth's orbit around the Sun. These numbers transcend human intuition so completely that they enter the realm of the genuinely incomprehensible. Yet they carry profound implications for the nature of reality itself. In an infinite or near-infinite universe, the laws of probability become inexorable forces that demand every possible arrangement of matter must occur not just once, but infinitely many times. The specific pattern of atoms that constitutes your body, the precise arrangement of neurons that generates your thoughts, the exact sequence of events that led to your existence, all of these would be repeated endlessly across the cosmic expanse. Somewhere beyond our observable horizon, there exists another Earth orbiting another sun in another Milky Way galaxy. The quantum fluctuations that shape the cosmic microwave background would eventually, given infinite space and time, reproduce the exact same patterns that led to our planet's formation. There would be another you, identical down to the last subatomic particle, experiencing this same moment of cosmic wonder as you listen to these words. The implications multiply beyond comprehension. Every possible variation of your life plays out somewhere in the infinite expanse. Every book that could be written exists in some cosmic library. Every symphony that could be composed echoes through some distant concert hall. Every scientific discovery that could be made has already been made by countless alien civilizations scattered across the boundless reaches of space. This possibility doesn't diminish the uniqueness of your experience, but rather emphasizes its absolute preciousness. Even in an infinite multiverse of possibilities, your consciousness remains the only one you'll ever directly know. Your perspective on existence is irreplaceably yours, making every moment of awareness a singular gift in the vast cosmic lottery of consciousness. The tools astronomers use to probe these cosmic depths represent humanity's most sophisticated attempts to transcend the limitations of direct observation. The cosmic distance ladder that allows us to measure galactic distances begins with geometric techniques like stellar parallax, where astronomers observe how nearby stars appear to shift position as Earth orbits the Sun. This foundational method works reliably out to about 1,000 light-years, providing the calibration for more powerful distance indicators. For greater distances, astronomers employ what they call standard candles, objects whose intrinsic brightness they understand well enough to serve as cosmic lighthouses. Cepheid variable stars, massive stellar giants that pulsate with clockwork regularity, provide distance measurements out to roughly 100 million light-years. Their pulsation periods directly correlate with their luminosity, allowing astronomers to determine distance by comparing apparent brightness with known intrinsic brightness. Beyond Cepheid range, Type 1a supernovas become the primary distance indicators. These stellar explosions occur when white dwarf stars accumulate matter from companion stars until they reach a critical mass and detonate with tremendous violence. Because this critical mass remains constant, these supernovas achieve nearly identical peak brightnesses, making them visible across billions of light-years while providing reliable distance measurements. The discovery that distant Type 1a supernovas appeared dimmer than expected led to one of cosmology's most startling revelations. These cosmic explosions weren't just farther away than anticipated. They were farther away because space itself was expanding at an accelerating rate. This observation revealed the existence of dark energy, the mysterious component that now dominates cosmic evolution and will determine the universe's ultimate fate. Dark energy comprises roughly 68% of the universe's total mass energy content, yet its nature remains completely unknown. Unlike matter, which becomes more dilute as space expands, dark energy maintains constant density throughout the growing cosmos. This strange property allows it to dominate cosmic evolution, despite being incredibly tenuous, perhaps equivalent to just a few hydrogen atoms per cubic meter of space. The simplest explanation for dark energy involves Einstein's cosmological constant, suggesting that empty space itself possesses inherent energy that drives expansion. According to this model, the vacuum contains a small but non-zero energy density that translates into a repulsive gravitational effect. As the universe expands and more space comes into existence, more vacuum energy appears, providing an ever stronger push that accelerates expansion. This acceleration has profound implications for cosmic observation and the growth of our observable universe. While light from previously unreachable regions continues arriving each year, expanding our cosmic horizon by roughly 1 light-year annually, dark energy simultaneously pushes distant structures beyond our future observational reach. Objects we can see today will eventually disappear from view as their recession velocity exceeds light speed. The cosmic microwave background provides our deepest probe into this ancient cosmos, carrying information from when the universe was only 380,000 years old. This primordial radiation fills all of space with remarkable uniformity, differing in temperature by mere microkelvin across different directions. Yet these tiny fluctuations map the density variations that eventually grew into galaxies, clusters, and the cosmic web itself. When astronomers analyze these fluctuations with sophisticated statistical techniques, they can determine fundamental cosmic parameters, including the universe's age, composition, and geometry. The patterns reveal that space is geometrically flat to extraordinary precision, supporting theoretical models that predict infinite spatial extent. They also provide strong evidence for cosmic inflation, the brief period of exponential expansion that may have stretched quantum fluctuations to cosmic scales. Modern space telescopes push these measurements to their absolute limits, detecting galaxies so distant we observe them as they existed when the universe was less than 5% of its current age. The James Webb Space Telescope has recently captured light from galaxies that formed when the cosmos was barely 400 million years old, revealing surprisingly mature stellar systems that challenge theoretical models of early cosmic evolution. These observations suggest that structure formation proceeded more rapidly in the early universe than previously thought, implying that the first stars were more massive and shorter-lived than current models predict. Each new discovery forces astronomers to revise their understanding of how quickly the cosmos transformed from its initially smooth state into the rich hierarchy of organization we observe today. Yet for all our observational sophistication, we remain fundamentally limited by the physics of information, transmission, and cosmic expansion. The observable universe represents an absolute horizon beyond which no signal can ever reach us, regardless of technological advancement. This cosmic censorship operates through the same mechanism that gives dark energy its dominance over large-scale cosmic evolution. Within our observable cosmic bubble, matter organizes itself into a magnificent hierarchy spanning dozens of orders of magnitude. At the largest scales, galaxies arrange themselves along filaments that stretch across hundreds of millions of light-years, creating a cosmic web that channels matter from nearly empty voids toward dense cluster regions. These filaments contain over half of all ordinary matter in the universe, serving as highways that guide cosmic evolution across vast distances. The Hercules Corona Borealis Great Wall stands as the largest known structure in this cosmic web, stretching across 10 billion light-years and containing hundreds of thousands of galaxies. This immense organization challenges theoretical limits on structure size, suggesting that either our models of cosmic evolution need revision or we're observing statistical fluctuations rather than genuine connected architecture. Our local supercluster, containing the Virgo cluster and thousands of other galaxies across 110 million light-years, occupies a modest position within this hierarchy. Recent mapping has revealed that even this vast assemblage belongs to the much larger Laniakea supercluster, spanning 520 million light-years and containing over 100,000 galaxies. These superclusters may themselves be organized into even larger patterns, though observational limits make such ultra-large structures difficult to study reliably. Within this cosmic architecture, the Milky Way appears almost quaint in its modest proportions. Our galaxy, containing perhaps 400 billion stars across a 100,000 light-year disk, represents a large spiral system, but nothing exceptional by cosmic standards. We orbit the galactic center at roughly 220 kilometers per second, completing one revolution every 225 million years, while the entire galaxy moves through space toward the Virgo cluster at hundreds of kilometers per second. Our solar system occupies an unremarkable position in the galaxy's outer regions, about 26,000 light-years from the galactic center in what astronomers call the Orion Arm. This location provides us with relatively clear views of the cosmic web beyond our galaxy, unobstructed by the dust and gas that would limit observations from regions closer to the galactic core. Earth itself represents an almost unimaginably small component of this cosmic hierarchy. If we could somehow scale the observable universe down to the size of our planet, the Milky Way would be smaller than a grain of sand. Our solar system would be invisible to the most powerful microscope, and Earth would be utterly undetectable by any conceivable measurement technique. Yet this cosmic insignificance contains within it something genuinely unprecedented in our observational experience. Through careful measurement and brilliant theoretical insight, a species confined to this tiny world has managed to map the universe across dozens of orders of magnitude, from subatomic scales to cosmic horizons. we've discovered the age and composition of the cosmos, traced its evolution from quantum fluctuations to galactic clusters, and glimpsed possible futures extending trillions of years into the cosmic future. This achievement represents something remarkable about the nature of consciousness itself. Against the overwhelming tendency toward thermal equilibrium and maximum entropy, local regions of space have organized themselves into structures capable of contemplating their own existence. We are not separate from this cosmic story, but integral expressions of it, temporary arrangements of stellar debris that have learned to ponder infinity and find it magnificent. The philosophical weight of these discoveries continues reshaping human culture in ways we're only beginning to appreciate. We are the first generation in human history to possess detailed knowledge of our cosmic context, to understand our place within the universal hierarchy of structure and scale. This knowledge brings both profound humility and extraordinary responsibility. Every act of scientific discovery, every moment of cosmic contemplation, every expression of wonder and appreciation contributes to the universe's growing capacity for self-awareness. Through us, the cosmos has developed the ability to study itself, to measure its own vastness, and to ponder its own meaning and purpose. We may be infinitesimally small compared to cosmic scales, but we represent the universe's method of understanding its own magnificent complexity. The darkness between stars is not empty, but filled with invisible matter and energy that shape cosmic evolution on the largest possible scales. Dark matter provides the gravitational scaffolding upon which all visible structure forms, while dark energy drives the acceleration that will determine whether the universe expands forever or undergoes more complex evolutionary cycles. These mysterious components, comprising 95% of cosmic reality, remind us how much we still don't know about the universe we inhabit. Yet our ignorance represents opportunity rather than limitation. Every unanswered question points toward frontiers waiting to be explored. Every mystery an invitation to deeper understanding. The universe appears to be not only larger than we imagine, but stranger than we can imagine, filled with phenomena and possibilities that stretch the limits of human comprehension. Modern cosmological simulations attempt to model this cosmic complexity, following the evolution of dark matter, dark energy, and ordinary matter from the earliest observable moments to the present day. These computational experiments successfully reproduce the large-scale structure we observe, providing confidence that our theoretical framework captures the essential physics of cosmic evolution. Yet the simulations also reveal how much cosmic history remains hidden beyond our observational reach. The vast majority of cosmic space and time lies forever beyond our ability to study directly, accessible only through theoretical extrapolation and statistical inference. We are like astronomers studying the ocean by analyzing a single drop of water, trying to infer the nature of currents and depths that extend far beyond our sampling ability. The search for life beyond Earth takes on new meaning when viewed against these cosmic scales. In a universe containing trillions of galaxies, each with hundreds of billions of stars, the statistical arguments for biological complexity elsewhere become compelling. Yet the vast distances between stellar systems create communication barriers that may prove insurmountable, leaving each conscious species isolated within their own cosmic bubble of awareness. These considerations transform our relationship with the cosmos from one of conquest to one of profound stewardship. We may be the only conscious observers in our local region of space, making us responsible for preserving and expanding the universe's capacity for self-understanding. Every scientific discovery, every act of cosmic contemplation, every moment of wonder contributes to the cosmic total of awareness and appreciation. The future evolution of cosmic structure depends on the ongoing competition between dark matter's gravitational attraction and dark energy's repulsive influence. Currently, dark energy dominates on large scales, driving acceleration that gradually weakens the bonds between cosmic structures. Over vast timescales, this process will lead to increasing cosmic loneliness as galaxy groups become isolated in an ever-expanding sea of empty space. Yet even this far-future scenario contains elements of wonder and possibility. The quantum vacuum itself may prove capable of spontaneous creation, potentially giving birth to new forms of organization we cannot currently imagine. The laws of physics themselves might evolve over cosmic time, opening possibilities for phenomena that remain forever beyond our present understanding. As you drift towards sleep tonight, remember that you're traveling through this cosmic immensity at tremendous velocity, carried by Earth's rotation, our planet's orbit, the sun's motion through the galaxy, and the galaxy's journey through expanding space. You are part of the universe's ongoing experiment in consciousness and complexity, a temporary arrangement of ancient starlight that has learned to contemplate its own cosmic heritage. The atoms in your body were forged in stellar cores billions of years ago, scattered through space by supernova explosions, and eventually incorporated into the rocky world where awareness learned to ponder its own origins. You carry within yourself the chemical legacy of cosmic evolution, a living library of the universe's journey from quantum fluctuations to conscious reflection. Every night, when you look up at the stars, you're seeing light that has traveled across vast cosmic distances to reach your eyes, connecting you directly to the cosmic web through the photons entering your retina. Some of that light began its journey before Earth formed, carrying information about cosmic conditions in the ancient past. You are an active participant in the universe's ongoing story of structure formation and conscious evolution. The cosmic web continues its patient dance of expansion and organization, carrying galaxies along filaments toward uncertain futures, while new stars form in nurseries scattered throughout space. Consciousness flickers briefly in scattered pockets of organized complexity, perhaps unique to our cosmic neighborhood, or perhaps distributed across countless worlds throughout the infinite expanse. Whether we are alone or part of a vast community of thinking beings, we remain privileged witnesses to the greatest story ever told. The universe may extend far beyond our ability to observe or comprehend, potentially infinite in its scope and eternal in its duration. Yet it has given rise to minds capable of grasping these possibilities and finding profound meaning within them. In seeking to measure the cosmos, we discover not just its incredible vastness, but our own remarkable nature as conscious participants in cosmic evolution. We are simultaneously the most insignificant specks imaginable and the most extraordinary achievements we know of in the observable universe. Through our curiosity and wonder, the cosmos achieves something unprecedented: the ability to contemplate its own existence and find it beautiful. Sweet dreams, fellow travelers, through the boundless expanse of space and time. May your rest be filled with visions of cosmic wonder, and your waking hours enriched by the knowledge that you are integral participants in the universe's magnificent experiment in consciousness and complexity. In these quiet moments of cosmic reflection, we touch something profound about the relationship between mind and cosmos, between the infinitely small and the infinitely large, between the temporary and the eternal. The universe awaits tomorrow's discoveries, and through our continued exploration, it will learn even more about its own extraordinary nature. Yet the cosmic revelations keep coming, each discovery more startling than the last. As we peer deeper into space with ever more sophisticated instruments, we're beginning to understand that even our most mind-bending estimates of cosmic scale may still be conservative understatements of reality's true scope. The universe appears to be not just vast, but inexhaustibly creative in its capacity to surprise us with new forms of organization and structure that challenge our most fundamental assumptions about what's possible. Consider the cosmic web itself, that magnificent three-dimensional spider web of matter stretching across billions of light years. When astronomers first began mapping large-scale structure in the 1980s, they expected to find galaxies distributed more or less randomly throughout space, perhaps with some minor clustering here and there. Instead, they discovered something that resembled the neural networks of a vast cosmic brain, with filaments of dark matter and ordinary matter creating channels that funnel galaxies along specific pathways through space. These cosmic highways aren't just pretty patterns in the sky, they represent fundamental organizing principles that govern how matter flows throughout the universe. Gas and smaller galaxies stream along these filaments, like traffic on superhighways, feeding the growth of massive galaxy clusters at the intersections where multiple filaments converge. The nodes of this cosmic web, where filaments meet and merge, become the sites of the universe's most spectacular gravitational gatherings, containing thousands of galaxies bound together by dark matter halos that outweigh visible matter by factors of 5 to 1. Between these filaments stretch the cosmic voids, vast regions so empty they make the space between galaxies seem crowded by comparison. These voids can span 300 million light-years of nearly perfect emptiness, containing fewer galaxies than you could count on your fingers scattered across volumes that would encompass millions of Milky Ways. They're not truly empty, of course. Dark matter threads through them in tenuous wisps, and the occasional lonely galaxy drifts through their depths like a ship crossing an infinite ocean. The Boötes void, sometimes called the Great Nothing, exemplifies these cosmic deserts. Stretching across 330 million light-years, it contains perhaps 20 galaxies in a volume that should host 2,000 based on cosmic averages. If Earth were located in the center of this void, we wouldn't have discovered other galaxies until the 1960s, fundamentally altering humanity's understanding of our cosmic context and perhaps delaying our recognition of the universe's true scale by decades. These voids are expanding faster than the cosmic average, driven by their lower gravitational content. As cosmic expansion continues, they grow ever larger and emptier, creating an increasingly foam-like structure where matter concentrates along thin boundaries, while vast volumes contain almost nothing at all. It's like watching soap bubbles expand, with all the soap collecting in the thin films while the interior spaces grow ever more empty. The mathematical beauty of this cosmic architecture becomes apparent when you realize it all emerged from tiny quantum fluctuations in the early universe, variations in density so small they represented differences of just 1 part in 100,000. Yet over billions of years, gravity amplified these whispers into the magnificent symphony of structure we observe today. The same fundamental forces that prevent atoms from collapsing have sculpted patterns spanning billions of light-years. Within this grand architecture, our Milky Way occupies what astronomers diplomatically call an unremarkable position. We're not at the center of any major structure, not part of any spectacular cosmic intersection. Instead, we find ourselves in what's known as the local sheet, a relatively flat distribution of galaxies that forms part of the larger Virgo supercluster. It's a cosmic suburb, if you will, pleasant enough but hardly the center of universal attention. This mediocrity extends to our galaxy itself, which despite its 400 billion stars and 100,000 light-year diameter, represents nothing particularly special by cosmic standards. The Andromeda Galaxy, our nearest major neighbour at 2.5 million light-years away, actually outweighs us by perhaps a factor of 2. When these two galaxies collide in roughly 4.5 billion years, the resulting merger will create what astronomers have whimsically named Milkomeda, a giant elliptical galaxy that will dominate our local cosmic neighbourhood. Yet even this future galactic colossus will remain a minor player in the cosmic hierarchy. The largest known galaxy, IC 1101, contains over 100 trillion stars spread across 6 million light-years. Its central supermassive black hole weighs as much as 40 billion suns, making it one of the most massive single objects known to exist. The galaxy is so large that light takes 6 million years to cross from one side to the other, meaning different regions experience noticeably different cosmic epochs. These extreme examples remind us that the universe operates on scales where our familiar concepts of distance and time begin to break down. When we say the Hercules Corona Borealis Great Wall stretches 10 billion light-years across, we're describing a structure so vast that light from one end takes most of the universe's age to reach the other end. It's like trying to have a conversation with someone standing on the opposite shore of an ocean that's expanding faster than sound can travel across it. The cosmic microwave background radiation offers our deepest glimpse into this ancient cosmos, carrying information from when the universe was a mere 380,000 years old and roughly 1,000 times smaller than it is today. This primordial afterglow fills every cubic centimetre of space with photons that have been cooling and redshifting for nearly 14 billion years. When you tune an old television to static, roughly 1% of that snow consists of these ancient photons, fossils of the moment when the universe first became transparent to light. The temperature variations in this ancient radiation are incredibly subtle, differing by only about 100 microkelvin across different patches of sky. Yet these tiny fluctuations represent the seeds from which all cosmic structure eventually grew. Regions that were slightly warmer than average had slightly higher density, providing the gravitational seeds around which the first stars and galaxies would eventually form. When cosmologists analyze these patterns with sophisticated statistical techniques, they can extract fundamental information about the universe's composition, age, and geometry. The data reveals that ordinary matter comprises less than 5% of cosmic reality, while dark matter accounts for about 27%, and dark energy dominates with roughly 68%. These proportions have remained remarkably stable throughout most of cosmic history, even as the absolute densities have changed dramatically due to expansion. The precision of these measurements represents one of humanity's greatest intellectual achievements. Using instruments no larger than a desktop computer, orbiting observatories have mapped temperature variations across the entire sky with accuracy measured in millionths of a degree. The resulting data allows cosmologists to determine the universe's age to within 1% precision and its overall geometry to extraordinary accuracy. That geometry appears to be remarkably flat, meaning that parallel lines never converge or diverge even across cosmic distances. This flatness strongly suggests that space extends far beyond our observable horizon, potentially stretching to infinity in all directions. In an infinite universe, every possible arrangement of matter must occur infinitely many times, including perfect duplicates of our observable region, scattered like islands in an endless cosmic sea. The implications of cosmic infinity challenge human comprehension, even more than the vast but finite scales we've been exploring. If space truly extends forever, then somewhere beyond our cosmic horizon lies another Earth, another version of human civilization, another you contemplating these same cosmic mysteries. The mathematics of infinity demand that every possible variation of existence plays out somewhere in the boundless expanse. From ancient stargazers who thought the heavens were within walking distance to modern astronomers mapping structures 10 billion light-years across, we've journeyed through humanity's greatest expansion of perspective. The observable universe, stretching 93 billion light-years and containing 2 trillion galaxies, may itself be just a cosmic droplet in an ocean at least 250 times larger. Yet within our infinitesimal corner of this vast expanse, consciousness emerged to contemplate infinity itself. We are simultaneously the most insignificant specks and the universe's greatest achievement, stardust that learned to wonder at its own cosmic heritage.